Thanks a lot for coming. I really appreciate that you chose this talk. As testers, we're faced with the challenge that we have to test more and more functionality in less and less time. Because successful software grows and we keep adding features. We're hardly ever allowed to remove features from our software. But paradoxically, because release cycles are getting shorter and shorter, we get less and less time to test more and more functionality. When I started in software quality analysis and quality assurance 15 years ago, most of the teams we worked with released once a year or 2 times a year. Now many of the teams we work with try to release on a weekly basis or every 2 weeks. And we still have to do a lot more work in that time. And I'm convinced that we can only do this if we get transparency into the black box of software testing. And by that I mean that we need to know more about what changed, so where are most likely new bugs, and on the other hand, where did we already test? Automated tests, manual tests, where did you already perform quality assurance? To be able to allocate our remaining test efforts better. And in this presentation, I want to present different analyses to get this transparency into the black box of software test. Now, before I start, please, if you have questions, don't wait until the end of the talk, but interrupt me immediately. Patrick is so nice to run around with a microphone, or you just shout in the question, I repeat it. And it needs not be a well-articulated question. It's fine if you have an opinion or skepticism or doubt. Testing is so different in different companies. So if you say, the stuff I say doesn't apply to you, please shout in, then we get this more interactive. And I'm happy if it gets more interactive. I don't need to do the slides in the order I brought them. So what do I mean by bringing transparency into the black box? I want to start with 2 examples that are not from software, but which I hope give you an intuition about what I'm aiming at. My first example is X-ray pictures. Everybody knows X-ray pictures. This is a kneecap. More specifically, this is my right kneecap after I broke it. This is the steel wire that puts together the pieces of bone, and the small things are the clamps that close the scar. Now, what does this have to do with QA? The first part, nothing. I mean, the accident and the surgery, this is all unplanned and doesn't feel like there's a structured process behind that. But the second part, in the second part, you have to go to a doctor, and what he basically does is QA. And for me, the interesting part was that the doctor didn't ask me where the pain was. He didn't take my temperature, he didn't take a blood sample. Instead, he just did this X-ray to see whether the change that the surgeon did resulted in what he expected to result in. And I would like us, as testers or as developers, to have a similar knowledge about what did we change in the software since we last tested it. The second example I brought is from football. This is a football heat map from the game of Bayern München. I'm from Munich. This is my team against Paris Saint-Germain in the Champions League when Bayern lost. Because outside of Munich, Bayern is not so popular. I thought I chose an example where Bayern lost. And here you can see which players spent how much time in which parts of the field. I'm not into football coaching enough to know if this is actually any useful or if it's just entertainment. But I find it ironic that I, as a football fan, know more about where my favorite players spent their time than I, as a tester, know if I'm responsible for a mission-critical system, where my own tests executed the system, or where other testers analyzed the system, or where the automated tests went. And what I would like to have is a similar level of knowledge about what did we test already, and how does it compare to the changes we did. So, and this is what I want to talk about in this talk. By test intelligence, I summarize the different analyses that analyze the data from our own development process to help us be more effective and efficient. And I chose 3 questions for this talk. I want to talk about where are untested changes, because we know empirically, we know from gut feel that in long-lived software, most bugs are in the areas that we changed recently. And we also know that from empirical research. And then I want to talk about where were most bugs in the past, because they are often an indicator about a problem in the development or test process. And then at the end, I want to talk about if we have a large test suite, which tests should we select now? And all based on your data. I want to do the talk in 2 parts. The first part is what data is there in a typical software development project so that we're all on the same page. And in the second part, I will talk about the analysis. And I will try to do both a research perspective and a practical perspective. And so that you know where the experiences come from. Some short background on me. I have 2 roles. I'm interested as a researcher. This is how I looked when I started my PhD. And I'm interested as a founder. This is how I looked when I came out of research. And I mean, revealingly, this picture shows that you don't immediately starve if you do a PhD in Munich. But that's not the reason I have it in here. The reason I have it in here is that I'm interested in 2 perspectives. As a researcher, I want to know what is relevant to measure. Because unfortunately, in computers, in software engineering in general, and in quality assurance in specific, we often measure what's easy to measure and not what's important to know. And in this role, I'm interested in what is really relevant to know. And in this role, I want impact. Because just an analysis doesn't change anything. If I stand on the scales every day, I won't lose any weight. If I run an analysis every night, I won't improve my software. So in this rule, I'm interested in impact. And last message on background, this is some of the customers we work for. And the key message I want to send is that this challenge that we have to test more and more functionality in less and less time is across the board. It's not limited to a single programming language or organization type or domain. So what is the data I'm working on? One data source is the version control system. It contains the source code and all the changes every developer did to the code base. And we can use that to compute what changed. And typically, if I talk to somebody who's worked with code before, then the image that immediately comes to mind is that of a diff. This is one of the functions in our code base. On the left side is the code I wrote. On the right side is what Lars did, which comments he added in the review. And I don't want to stress the details. What I want you to think about is that although we usually use a diff on a very fine-grained level, the information is there about the entire system. So we can use that information to compute for the entire system for a large time frame what changed. For example, we can compute what changed since the last release. And to give you an impression how much data we have, I want to use a so-called tree map as a visualization. The idea is very simple. Every rectangle here corresponds to a component in our system. The bigger the rectangle, the larger the component in lines of code. And now I move in. The components are still in the same place. And the small black rectangles are files now. And even further in, now the tiny rectangles are functions or methods. And it still holds, the bigger the rectangle, the larger the corresponding function or method in lines of code. And now we can use this visualization to see what changed. Now gray means unchanged since the last release. Red is new code and orange is changed code. This system is a business information system written in C# by 30 developers. And at the time of analysis, that was pre-Agile transformation. There were 6 months between 2 releases. And this is the changes the day before the release was supposed to go live. So 30 people had worked on that for 6 months. And you see easily that in this area, not so much changed, but a lot of work has been done in this area. So when we test this, we probably want to make sure that we are especially careful in these areas, because a lot of changes or new functionality have been added here. The second data source I want to work with in this talk is test coverage. And again, typically, when we think about test coverage, we think about white box testing or Unix testing on a very fine-grained level. And how we typically see it used in practice is that a developer looks at a single method. This is an example, again, in Java from a from an open source system called BioJava. It does some bioinformatics stuff. And we ran the unit tests, and everything that's green means, every line that's green means that the unit test executed that line. And the typical use case is for developers that write unit tests to look at the test coverage to see are there any test cases they're missing. In this case, for example, this line was not executed. Now you can think about, do we need another test that does this? This is not the use case I want to talk about today. Instead, just like with changes, we can lift this for to the entire application. And there's no reason that we can only look at automated tests. The code coverage profiler, the software that captures code coverage, doesn't care at all whether it analyzes automated or manual tests. To drive that home, this is an animation where we do a manual test in a paint program. On the right, you see which areas of code are executed exactly when this part in the UI happens. So we can capture code coverage for manual tests and for automated tests, and also look at that to see which areas did we test during our tests and which didn't we. So now we're all on the same page, and now we can use the change information and the test coverage to answer interesting questions. And the first one, which I think is the most obvious one, is how do the changes relate to what we actually tested? Where are, or in other terms, where are untested changes? Because, why do I think that's relevant? Because there's an entire research area called defect prediction that has spent several decades on trying to predict where bugs will occur in production. And they've looked at hundreds of systems, at thousands of metrics, and done a lot of research, and one of the not so surprising results is, for long-lived software, most of the field bugs are where things change. Not so surprising. Surprising for us, though, is how much code slipped through production, into production untested. When we did the first analyses like this, 50% of the changes that were made slipped into production untested. And how do we know that? Because we mesh those data sources together. So we can get what changed from the version control system and what did we test from the test coverage analysis. And for this system, for the 1.5 million lines of C# code, there were automated tests, both unit tests and integration tests, and there was a test factory that performed manual regression tests for 3 weeks, 5 people, thousands of test documents. And this is the aggregated test coverage. And gray means not executed in test, and green means executed in test. And now, how does this relate to each other? This is what this tree map shows. Now the colors mean the following. Gray means unchanged, independent of whether it was executed in test or not. The colorful rectangles are the change in new code, and only if it's green was it ever executed during test. Now what does that mean? If it's green, we know we executed it. We don't know how many bugs there are still in there, unfortunately. This is the fundamental limitation of test coverage. We know we executed it during test. We don't know if we found all the bugs. However, the inverse is as trivial as true. All the red and orange stuff, we know we can't have found a single bug because we never executed that during testing. Not in the automated tests, not in the manual tests. And this tree map was computed the day before the planned release. And now, if you look there, there's big areas that contain a lot of modified and new code. In this case, tens of thousands of lines in every component. And they were not tested at all. That needs not be a problem. It could be that this is functionality which for some reason we don't need in the next half year. This was not the case here, though. So when we looked at that, the team decided to postpone the release and do that at a later point. So our goal here with test gap analysis is not to get everything green because it must be green, but instead to allow a conscious choice whether to release software like that or whether to postpone it and do further tests. Now, This is on the level of the entire system. This is interesting for somebody who's responsible for the entire system, but as an individual developer, individual tester, I'm often interested in a smaller bit of the system when I'm not responsible for the entire functionality. So I want to include a third data source called tickets. And tickets is an overloaded term. By that I mean a description of a unit of work in Jira, for example. In some teams it's called ticket, sometimes bug, issue, change request, user story, whatever. When I say ticket, please translate that to what it's called in your team. And most teams we work with, when a developer commits a change, they have to mention which ticket this is for. And that allows us to extract all the code areas that were touched during the implementation of the ticket and lift all this information to the level of a single ticket. This is a screenshot from our own development. And on the right side, you see the test gap. And in some tickets, all the methods have been tested, in some not. And then we can drill down to see this is the methods that were modified for this ticket, which is way less than the entire system. And then you can look at that, and because the ticket contains the domain description of what the change is about, our experience is that it's much easier to prioritize them and to take responsibility for what else needs to be done. Today in the keynote, we were asked to take responsibility. And I think, and one area where we often have to take responsibility is whether to close a ticket. Do we think it's implemented and tested sufficiently so that we can ship this functionality in the state it's currently in? And my experience is that it's much easier to take responsibility when we have the transparency about what changed and did we test that already. And part of our definition of done in our own development process is that we can't ship a ticket while it still has non-trivial test gaps. Now, the tricky word in that sentence was no non-trivial test gaps. What does non-trivial mean? And in that case, if it's a very short method that only writes or reads a single field, or a constructor that initializes fields, that's fine if that's not tested because it's so little code that it's correct, probably correct by sight, but everything else needs to be tested either manually or automatically, otherwise we can't ship that. And our process enforces that because as a developer, I can't merge a ticket. The reviewer has to do that, and the reviewer will check whether that is tested or not. So let me wrap that up. For test gap analysis, I'm interested in, I extract what changed from the version history, what was tested through test coverage analysis, and then we can look at that at the level of the entire system to see if there's any test gaps, or for an individual ticket, are there any test gaps? Please.
Yes. Sorry, not used to microphones. Yes. So it might be a silly question, but I just need to put it out there. So this is a tool that you're using to do this analysis, right? So that means that you feed the tool with, this tool is reading, okay, the component of the system that you're testing, and then you also have input from the test cases that have been created and executed, and what else? And also the automation one, right?
Yes. Actually, to compute this, we don't need to know which test cases were executed or whether they were automated or manual. We just observe the system under test while the tests run. So maybe this makes it more tangible. If I start this animation, the coverage profiler, there's coverage profilers for all the big programming languages. They can capture what happens in the software at the time of test. So our coverage profiler doesn't know that this is a manual test that's been executed, but it can still capture which parts of the system are executed.
So also this profiler is also reading when it gets the information from the full information of the system, it's reading the code.
Yes.
Okay. Yes.
Thanks. Further questions, because now this kind of wraps up test gap analysis before I go on now to the perfect time for test gap analysis questions. Thanks for the question.
Thank you.
Thanks.
So what I want to ask is, when we say that we cover some part of the code with the test, we can, I mean, I'm sure people would agree that it can be much more complicated than that. Just so that we've moved from, when we run this profiler, we see that some of the code has been run, doesn't mean that we have covered all the cases. So to identify just saying covered or not covered, or executed in test or not executed in test, how do we differentiate between that? Because just running one test on a piece of code doesn't mean that you have coverage. But here, do we differentiate between that, or is it just, you know, a test has run, so we just say that this part was covered in testing?
That's an excellent question. Let me rephrase. If we know a method was covered in a test, we don't know about if there's different cases, different test cases that should test that to make sure it really works. We don't know how many of them ran. That's completely true. And there's a technical answer and an experience answer to that. The technical answer is there's different types of test coverage. You can measure it on a method or on a statement or on a path, or you can have decision coverage and branch coverage. And it basically breaks it down to a final level. But the fundamental issue that we only know what was covered and not what was really tested remains. But my experience answer is that usually when I show this map for the first time, people, I often get the question, but there's a huge method of 20,000 lines. Maybe only the first line was executed and it's green here. That's true, that's not very accurate. However, there's so many test gaps here that the team didn't manage to close them in the available time anyway. So yes, there's a limit to how much we can know from there's something green, but I'm really interested in, are there any big gaps? And here we see there's tens of thousands of lines that were not covered, and this is the thing to focus on now, because there was a fundamental issue in the test planning process. But sometimes teams start with a more coarse-grained level and then use a more fine-grained level of coverage when they're more mature. But often I don't hear the question again when they see how many test gaps they have in the code. And this sounds a bit mean, but it's not because of a lack of discipline, but because software development is so complex. We ran a study in our own team, and our own team has a comparatively easy test coverage challenge because it's a rather small team. There's 60 people developing in our company, and it's very homogeneous. There's little churn, and everybody who's tested is also a developer. So it's probably easier than otherwise. And we had a research paper where we tried to measure, or where we measured how many test gaps we had in our own code. And the result was many, if we don't use a specific analysis for that. Because it's just so complicated, there's so many cases and so much moving parts in a large project that you won't, just by discipline or guidelines, avoid test gaps.
Why do we need to know this in all these gaps in the system? Is this something that we can fix or improve?
Excellent question. Why do we need to know this as testers? Because it tells us where do we need to do more testing. And if we don't know what the code is, then we can see through the tickets who developed that, and then we go to the developer and ask her or ask him, what did he do here? What is the functionality? And then I can think about what is a good test to do here. Patrick, do you have an overview who was next?
Yeah. Hi, my name is Attila, and I really like this because it relates to my experience from embedded system, where I wished that we could measure coverage. My question would be, I had the experience that where we had like 100% coverage of the code, but still the functionality was not that what was doing. Is there a way somehow to relate this to the functional coverage? Or did you have experience that although the code was tested, still the program was not doing what you expected? Thank you.
Also, thanks for the question. I mean, sometimes you said your experience is from the embedded domain. I know some embedded domains where there's a law that you have to have a certain percentage of coverage, otherwise you won't get the certification to release their software. Yeah, or avionic and so on. And in those domains, we've seen test suites that don't have a single check, that don't have a single assert. They only produce coverage. And they obviously not so useful because they won't find many bugs because they don't test anything. And I think a manual review of the test is a good idea then. And more academic answer would be mutation testing, where you automatically introduce bugs into your software and then run the test suite to see if it finds the bugs. But often it's a factor of 1,000 or 10,000 slower than the automated test suite. So I think much more pragmatic in practice is to look at the test to see if they actually test something. Also, this is never an expert replacement tool. This is always an expert support tool. We want to give you the information to be more considerate. But this, I think there's a limit to what you can automate here in terms of interpreting that. Thanks, Attila.
Yeah, so I got the mic. Here. Hey.
Thanks.
Yes, so when you've been working with the results of this, have you had instances where you really cannot reach the code with tests? And how does that happen? What do you do then?
Also a very interesting question. Sometimes there's unreachable code, where the code is basically dead because it can't be run anymore. And then you can probably simply delete it. Because if a user cannot execute the code, then probably you don't need to test it. We have had one instance where, due to a bug, it couldn't be reached. But then the fix was to make this code reachable. There's another class of code. Often in long-lived software systems, there's useless functionality, which would still be reachable, but which nobody needs anymore. And just as a tangent on this, you can run the same analysis in production. And for some systems, we've analyzed this for 3 years in production, just what was executed. And we've seen that some parts of the functionality were not executed in 3 years. And this probably means it can be deleted or isn't as important in testing. But this always requires a lot of trust in the analyses. And with all the companies we've done that, we first run the analyses and test. But this, like the question, is the stuff actually reachable? Is it still useful? Is something that often comes up if you sit together with a tester and developer and look at which areas are this actually, which functionalities behind that. Is that still important? Do we still need to test it, or can it be removed? And sometimes deleting code is a valid outcome of that discussion. I can repeat it. Is it a plug-and-play profile, or does it require integration with the code? That depends on the programming language and the target platform. Every different language has a different profiler. Sometimes it feels like plug-and-play if it's like Java or C# or SAP, if it has a virtual machine. If it's embedded, then sometimes there's hardware profiles where you can plug a switch into the processor and don't need to change anything of the software, and there's guarantees that the timing behavior of the software is still the same. And then you need a big hardware thing to convert the electricity into a coverage report. But sometimes you need to run a so-called instrumenter that changes the source code and recompile. So that's the short answer. The long answer, if you want to talk afterwards, you can tell me what languages you're interested in. I can give you more details. Last question, yeah. Then I. How can we deal with code that is not useful anymore, but nobody dares to delete it?
Yes, because it's still executed, like batch jobs.
Like what? Batch jobs. But maybe if the batch jobs are still executed, they're still useful? I don't know. What really surprised me, when we had this analysis where we showed that 2/3 of a system were not used in 3 years, we expected people to delete them. They did not delete them. Why not? Because often as a developer, nobody praises you if you delete 1 million lines of code. But if you delete 1 line too much, you're in trouble. So what they did was a virtual deletion. So they moved this code into a folder called to be deleted and had a user prompt in front of that. So when anybody would execute that, there would be a pop-up saying, this will be deleted. If you still need it, call here or click here or whatever. And then after a year of that, when nobody did anything, they then deleted this. So maybe that's a workaround here. And I think that the root cause of that is a fundamental organizational issue, but that was not in our power to change, and this kind of virtual deletion helped avoid waste of refactoring that code that nobody used and then deleting that later. Thanks a lot for the discussion and the questions. I really appreciate that. I now want to do the rest of the talk so that we still have some time at the end to do the other questions. Our second question I want to look into is, where were bugs in the past? And for that, we analyzed the version history to see where were bug fixes in the past. And this tree map is from another industrial system. Again, every rectangle is a file in this case. Size corresponds to size of file and lines of code. And what I did here is for the last, I think, 3 years in this analysis, I analyzed where were bugs fixed and which files were touched during the fix of a bug. And then the darker the shade of blue, the more often these files were touched during a bug fix. Now, this is not entirely accurate. Sometimes if you fix a bug in one file, you do some auxiliary changes in some other files, and all those files are treated equally here. Still, we get some signal because I mean, it's thousands of changes. There's some noise, but also a lot of signal. And if you look here, there's this block in the middle that for some reason is a darker blue than the rest. Here's a bit more bugs, but a lot of bug fixes were here. Now, what happened here? Same system, same tree map layout. Green means coverage of automated tests. And if you put the two things on the same page, you see, as you already saw, that the part that has more bug fixes has way less automated coverage. Now, what happened here? I spoke with the developers in that system, and this is the back-end code, and this is the back-end code, and this is the front-end code in JavaScript. And thanks, Patrick. They never made the effort at that point to lay the foundation to make it easy to write automated scripts, automated tests for the UI part, for the JavaScript part. And so they sometimes manually tested that, but then regressions wouldn't be caught, and a bug was created by a user, and then it had to be fixed. But presented with that data, it became obvious that there was a process problem, that it was too hard to write unit tests or automated tests for the UI part, and that convinced management to plan, budget for changing that. And when we analyzed that later, there was coverage here as well, and the bugs were more evenly spread. I have this example in here because this is a very cheap analysis in terms of how much effort you have to do, because it's completely automated. And sometimes it's a hit or miss thing. Sometimes you see something interesting like here, sometimes not. You don't know before you do the analysis where you find the bugs, but it's a very, very simple thing to do. Now, any questions on this? Yeah?
How is the analysis done after the tooling? Do we have to do it manually, or do we get a report of the differences?
Thanks. We did this fully automatically. We extracted all the commits from the version control system and the information which commit was a bug or not, or which files were changed. You can't do that manually because it's so much data involved. Thanks.
I saw that the other blue area and on the right side have a lot of automation.
Yes.
You know the reason of that?
That's a good point. I don't know. I would have to look that up. Sorry. Thanks for the two questions. The last thing I want to talk about is if you have many tests and can't run all of them now, which provide most of the value. And I think for manual tests, this has always been a problem. For automated tests, when I started out, most of the teams, 15 years ago, most of the teams were facing the challenge that they didn't have enough automated tests. Happily, many of the teams have a lot of automated tests now, but we have some customers who have tens of thousands or 80,000 tests, and they run days or sometimes weeks to execute all of them. And if I break something and a test tells me 10 minutes later, it's easy to know which change broke the test. If I have to wait an entire month, it gets so much harder to know what broke the test. And the basic idea of the test impact analysis, which I want to present now, is to measure for every single test case which code it executes. And then, based on a change, select those tests that run now. I want to show you with our own data. This is our own system. And for one ticket, this is the changes that Andreas, who implemented this ticket, made. Our system is a program analysis software, so whenever a programming language we analyze changes, we need to adapt. So when Java received closures as a language feature, this is what we had to adapt to still be able to understand Java with closures. Red is new code, orange is modified code. Now, what I now do is run our tests in a time lapse. Every second I run 30 tests. All the methods that one test touches are green and are white and then fade to green. I start that now, and you see that there's a lot of activity here, and then there's other areas that get tested. And I hope this gives you a bit of an intuition how much data there is we can work with if we capture test coverage on a test-wise basis. And also, it shows you everything that was tested gets green, but we've run hundreds of tests now, and most of our changes are still orange and red. This shouldn't be a surprise. When we built the other tests years ago, nobody built tests for Java closures because we didn't know there would be a thing such as Java closures. And of the, I think, 7,000 tests we had back then, only 4 executed code that was modified or added. And I mean, the other ones can't find a new bug. If they don't execute any of the changes, they can't find a new bug. This is wasteful if we always execute all the tests, but on the other hand, it's a good potential for optimization if we only execute the tests that run through modified code. And that's the basic idea of test impact analysis, where we throw away all the tests that are not impacted by changes, and then reorder them in such a way that failures are early in the process. And let me just go quickly through the remaining slides. We've done a lot of research projects to see how quickly we can find how many bugs. And if we run test impact analysis, we find 80% of the bugs that the entire test suite finds in 1% of the time, and 90% of the bugs that the entire test suite finds in 2% of the time. However, if we want to make sure that we find all the bugs that the entire test suite finds, we have to run the entire test suite. So what we usually do is, if a customer runs the entire test suite every weekend, they still run the entire test suite every weekend, but now run the impacted tests every hourly build or every commit trigger build, so that you find 90% of the bugs quickly and the remaining 10% as you did on the weekend. So this wraps up my talk. If you want to see this live, tomorrow we have a demo, Jakob and I, same time in room 1E. And as Pepe said, please give us a hard time. Lavinia, Jakob, and I, we are outside at the booth and are happy to go into more detail, also including test coverage profilers or whatnot. And this is my first time at Agile Testing Days. I don't know how well our topics and the research stuff works here, so please give us feedback so that we can improve, and if we are here another time, make a talk that's even better. Thanks a lot. I think we have 3 more minutes. There's a question.
Amazing talk, thank you. It has jogged so many muscles in my brain that I have so many questions, but I will just stick to the one which might be boiling in our brains right now. Is there an open source or community edition of this profiler we can get our hands on so that we can play on our code?
Thanks for the question. Our profiler for Java and C#, they are open source and free, but the software that uses the data and then produces those charts, you have to pay for that. That's our business model. We sell licenses for the software, but there's a free edition for 3 months where you can try out all of that. And it's free for open source and research and teaching.
Thank you for your excellent talk. I have a question regarding the test-wise coverage. So it's mainly for the automated test or also for the manual test?
Also an excellent question. It's possible for both. It's easier to capture for automated tests, but we have customers that capture coverage for manual tests as well. Mm-hmm. For example, Zeiss, who's also a sponsor here, they build the microscopes, and they have a manual test for the microscopes, and they capture a lot of coverage for the manual tests, and now if they have a hotfix, they can select the manual tests that execute the changes.
Okay, thank you.
Can you make a difference between the manual and the automated test when you run it on a system? In the results, can you tell which one was manual and which
Can you tell which one was a manual test and which one was an automated test? Yes. If you capture the coverage separately, and most of the teams that use that capture the coverage separately, so that you can look at all the results for the manual tests, for the automated unit test, for the automated integration test, for the automated end-to-end test, and also for the aggregate of that. Okay, we are out of time. Thanks again.